Online activity, GPS Geodesy. Today we will learn about what geodesy is and how we measure the motion of the Earth with different methods. Our activity will be an application of the Global Positioning System, GPS, to the tectonics of the Pacific Northwest, specifically the Cascadia subduction zone. What is geodesy? Geodesy is the science of accurately measuring and understanding three fundamental properties of the Earth: its geometric shape, its orientation in space, and its gravity field, as well as the changes of these properties with time. Geodesists also study geodynamical phenomena such as crustal motion, tides, and polar motion. For this, they design global and national control networks using space and terrestrial techniques while relying on datums and coordinate systems. If you know the size or shape of the Earth, you should also be able to figure out where you are on the Earth. Pythagoras and Aristotle postulated that the Earth was a sphere. Eratosthenes calculated the circumference of the Earth. Given a little math, in this case trigonometry, which is the spatial relations of triangles, the lengths of the sides of triangles, and the angles between each of the sides, we can calculate the distances between objects. This is known as triangulation. Here is the USGS triangulation network that was in place prior to the development of GPS-based geodesy. Thomas Jefferson founded the Coast Survey in 1807, which was renamed to the Coast and Geodetic Survey in 1878. Currently, the National Oceanic and Atmospheric Administration conducts the activities that these prior agencies accomplished. On the right, here is an example of a triangulation survey from the 1940s that was updated in the 1990s using Global Positioning System or GPS measurements. Sometimes the Earth moves, like it does during earthquakes. A geodesist can use a triangulation network to determine the distance that has been offset during the earthquake. The photo at the right shows how a fence was offset during the 1906 San Francisco earthquake. We are not always lucky enough to have an offset fence to measure, so we must use a triangulation network. Here is an example of the triangulation network established in Northern California to evaluate motion along the San Andreas Fault. This type of network was used through the 1980s until technology developed to make measurements more quickly. Now we can make measurements constantly using GPS. We can make geodetic measurements using a triangulation network. These measurements can be made in between earthquakes to determine the rates of motion between plates. Also, they can be made before an earthquake and after an earthquake to determine how much the fault moved during the earthquake. One simply measures the distance between different locations to see which line lengths got longer and which ones got shorter. For example, in this example, the line length between A and C and between B and D got longer, while the distances between A and B and C and D remained the same length. What do you think this tells us? GPS geodesy is made up of measurements between satellites and ground stations. The ground station's position can be determined through space-based triangulation. Precise clocks are critical for determining the distance to the satellite. Using known frequencies and the precise time the signal left the satellite allows for calculating the distance to the satellite from the ground. Global Positioning System, GPS, ground stations track orbiting satellites' path. In addition to locating a benchmark with respect to GPS satellites, having well-located receiving stations on the ground allows for greater accuracy in determining one's position. Given the number of precisely located ground tracking stations currently operating, 24 hours of continuous data will return a horizontal position to within 2 to 4 millimeters. Given enough measurements between a series of points scattered across the landscape, we can determine the relative position between 2 points. In this case, we don't need to take any measurements directly between points J and K. We simply take measurements along each edge of these triangles. This is the theodolite used in the Great Survey of India, and it weighed 1,000 pounds. If K moves relative to this triangular network, our distance measurements alone can tell us how much K moved. If we know the time between the measurements, we can calculate the rate of motion for point K. How do we calculate velocity rate? That's right. Recall that a velocity rate can be determined by dividing distance by time. If it took 1 hour to drive to Portland to see a lecture on earthquake hazards along the Cascadia subduction zone, which is a 70-mile trip, what is the average velocity? That's right, 70 miles per hour. What if point K moved 10 meters during a period of a year? What is the velocity rate? That's right, 10 meters per year. What would the rate be if we used velocity units that geologists typically use for calculating plate motion rates, like millimeters per year? That's right, 10,000 millimeters per year. Next, let's see how we would use a triangulation network, a network of triangular measurements, to calculate the rate of motion of a point located on Earth. We will use a network formed by the positions of 4 points, 1, 2, 3, and 4. We will calculate the velocity rate of motion for these points given the time period between our distance measurements. The second distance measurements are collected 10 years after the first distance measurements are collected. Step 1. Time equals 0 years. Here is our triangular network of points 1, 2, and 3. Step 2. We have measured the distance between points 1 and 4, which is 2.236 meters. When we draw a circle of radius 2.236 meters centered on point 1, we know that point 4 lies somewhere on the circle. Step 3. Next, we measure the distance between points 2 and 4 and draw a circle centered on point 2 with a radius of 1.414 meters, the distance between points 2 and 4. We know that point 4 lies somewhere on this circle. Because the point also lies somewhere on the circle drawn around point 1, and there are only 2 locations that lie on both circles, point 4 must lie at one of these 2 locations. We need one more measurement and one more circle to be able to determine where point 4 is so that we can triangulate this position. Step 4. Next, we measure the distance between points 3 and 4 and draw a circle centered around 3 with a radius of 3.162 meters, the distance between points 3 and 4. We know that point 4 lies somewhere on this circle of radius 3.162 meters. Since we know it also lies on the other two circles, we must conclude that point 4 lies at the intersection of these three circles, which leaves us with but a single solution. Step 5. Now place a dot at the intersection of these three circles and label this point 4. Step 6. I draw lines with lengths of the radii from all three circles. This illustration shows how the distances between any of each 3 points forms a triangle. This also illustrates how we can determine relative location of any 3 points given that we know the distances between each of these 3 points. We will now wait a decade and make a new series of measurements to determine if any of these points moved over time. Sometimes Earth's crust moves and we need to make measurements just like this to find out how much it moved. Step 7. Based on a distance measurement between each of 3 points 1, 2, and 3, we have determined that points 1, 2, and 3 are still in the same relative position. Next, we will make measurements between these 3 points and point 4. Step 8. We have measured the distance between points 1 and 4, which is 3.606 meters. When we draw a circle of radius 3.606 meters centered on point 1, we know that point 4 lies somewhere on this circle. Step 9. Next, we measure the distance between points 2 and 4 and draw a circle centered on point 2 with a radius of 3.162 meters, the distance between points 2 and 4. We know that point 4 lies somewhere on this circle. Because the point also lies somewhere on the circle drawn around point 1, and there are only 2 locations that lie on both circles, point 4 must lie at one of these 2 locations. We need one more measurement and one more circle to be able to determine where point 4 is so that we can triangulate this position. Step 10. Next, we measure the distance between points 3 and 4 and draw a circle centered on point 3 with a radius of 1.414 meters, the distance between points 3 and 4. We know that point 4 lies somewhere on this circle of radius 1.414 meters. Since we know it also lies on the other 2 circles, we must conclude that point 4 lies at the intersection of these 3 circles, which leaves us but a single location. Step 11. I now place a dot at the intersection of these 3 circles and label this point 4. Step 12. I draw lines with lengths of the radii from all 3 circles. This illustration shows how the distances between any of each of these 3 points forms a triangle. This also illustrates how we can determine the relative location of any 3 points given that we know the distances between each of these 3 points. We will now compare the relative motion of point 4 between time A and B, which was a decade. Step 13. We can now measure the distance between point 4 at the different times A and B, which are a decade apart. We find that this distance is 2 meters. Step 14. What is the distance between point 4 at time A and point 4 at time B 10 years later? That's right, 2 meters. What is the time between time A and time B? That's right, 10 years. Now we simply divide distance by time. Go ahead and do this. 2 meters divided by 10 years equals 0.2 meters per year. Or, in units we commonly calculate plate and fault motion rates, 200 millimeters per year. Geodesy can be used to measure the motion of Earth due to movement of magma in the subsurface. Here at the right is a cross-section of Earth showing the magma chamber between Long Valley Caldera in Southern California. The movement of magma at depth can cause the surface of the Earth to move also. This information can help us determine if there might be a future eruption. In the 1990s, there were lots of volcanic earthquakes in this region, so the USGS set up a triangulation network to measure the ground motion. Long Valley Caldera. This is a plot of the velocity rates as measured around the Long Valley Caldera, which last erupted 760,000 years ago. As the magma expanded around the volcano, this caused the crust to expand upwards and outwards. The motion vectors tell us the direction and rate of motion at various locations. What can we say about the motion of the crust in relation to Long Valley Caldera? The motion vectors are all pointing away from the caldera, suggesting the crust is moving outwards away from the caldera. Is there a pattern in the velocities? Yes, the geodetic motion is greatest nearest the caldera and diminishes at the further distanced locations. Here is a plot showing the vertical motion at benchmarks throughout North America. What causes this vertical motion? This motion is caused by the melting of the ice sheets from the last ice age. During ice ages, the ice pushes down on the crust and the crust sinks into the mantle. After the ice melts during the interglacial period, the crust has less of its downward pushing load, so it rebounds upwards. Where's the crust rebounding the most? Yes, in Canada. Why do you think this is? Yes, this is where the greatest amount of ice thickness was in this map region. This is a plot that shows the earthquake cycle. Geodesists use triangulation measurements to evaluate the crustal motion during different parts of the earthquake cycle. The coseismic time is the period of time during the earthquake. The interseismic time is the period of time between the earthquakes. The pre-seismic time is the period of time before an earthquake. And the post-seismic time is the period of time after an earthquake. This plot shows the motion of a location on a tectonic plate near a fault. During the interseismic period, the motion of the plate is to the north. During the coseismic period, the motion of the plate is to the south. There's a short period of time after the earthquake, during the post-seismic period, when the plate slowly changes direction from south to north. Think about why this might happen We can discuss this in class.
Precise measurements gathered from GPS stations over time have helped us better understand earthquake hazards. For example, prior to March 11, 2011, scientists noted that hundreds of GPS receivers in Northern Honshu had been recording steady westward movement of the stations along the coast. Because the shallow portions of the subducting and overriding plates are locked by friction, the leading edge of the overriding plate was being forced west, uplifting slightly as it was compressed, therefore storing elastic energy. Elastic rebound during the earthquake caused stations along the coast in Miyagi Prefecture to jump east by as much as 14.5 feet, or 4.42 meters. The abrupt uplift of the eastern edge of the overriding plate near the Japan Trench produced the catastrophic tsunami. We now know that a mirror image great earthquake and tsunami happened on the Cascadia subduction zone on January 26, 1700. Evidence for the earthquake of 1700 comes from Native American oral histories, dating of ghost forests on the Pacific Northwest coast, and arrival of a well-documented orphan tsunami that arrived in Japan 9 hours after the earthquake. Over the past decade, the compression of the Cascadia continental margin has been confirmed by GPS data collected by EarthScope's Plate Boundary Observatory. The coastline, near the Juan de Fuca North America plate boundary, is moving northeast more rapidly than the inland areas, while GPS stations east of the Cascade Mountains are not moving. Now let's zoom in to the GPS station at Cape Meares Lighthouse on the Oregon coast and see how it's moving. The graph shows the position of this GPS station each year compared to its starting location in 2000. The sequence of data points documents the northeast motion of Cape Meares at 0.4 inches, or 10.5 millimeters, per year. From 2000 to 2013, Cape Meares has moved northeast about 5.1 inches, or about 130 millimeters. Since the Cascadia earthquake in 1700, Cape Meares has moved by almost 11 feet, or 3.3 meters. What does this imply about the leading edge of the Cascadia continental margin? Let's look again at a cross-section with graphs reflecting the movement of each GPS station. We'll use a spring to represent the elastic nature of the overriding plate. Coastal stations are pushed northeast by the Juan de Fuca plate at a faster rate than inland areas, so elastic energy builds within the leading edge of the overriding plate. Just as the westward motion of GPS stations in Japan recorded growing stress on that subduction zone prior to the 2011 earthquake, the steady movement of GPS stations in coastal Cascadia also indicates growing stress. Although friction between the Juan de Fuca and North American plates has prevented our spring from releasing, when that friction is ultimately overcome, the resulting earthquake will cause Cape Meares to jump southwest, back near the position after the Great Cascadia earthquake of 1700. Here's what that elastic rebound process would look like in map view. Although we can't predict when or where the next earthquake will happen along the subduction zone, we are certain that one will eventually occur. Understanding the meaning of these GPS observations should motivate us to build an earthquake and tsunami resilient Pacific Northwest. In this animation, the three grids portray plate interaction and deformation in three zones of a subduction region, which include the lock zone at the leading edge of the overlying plate, a transitional zone that locks for approximately 14 months at a time, then slips back a little before continuing its push inland, and the zone far inland from the locked portion of the plates that sees little to no deformation. The grids below each GPS receiver represent compressional stress on that region. The first graph shows the leading edge of the continental plate is locked with the subducting slab, thus gets shortened, building elastic potential energy. The graph shows steady rate of change as the land is being forced relentlessly inland. It will ultimately release the built-up strain, resulting in a great earthquake. Graph 2 shows the land being forced inland due to friction between the plates, but it occasionally backslides along the plate boundary, releasing some of its stored elastic energy in mild seismic tremors spread over a period of days to weeks. The sawtooth pattern on the graph reflects the forward-backward motion of the GPS station on the surface. The third station does not move, and the grid shows no deformation, so the graph is flat.
Plate boundaries at different times during the earthquake cycle. A. Sumatra. These motions of the upper plate are in the same direction that the upper plate moved during the earthquake, or opposite of the direction of plate convergence at this subduction zone. Why do you think this is the case? Yes, this is an indication that we are in the post-seismic period. Since the plate is still slipping, the motion is in the direction of the slippage. B. Chile. These motions are in the direction of plate convergence in the north and opposite the direction of plate convergence in the south. What do you think would explain this? Yes, the southern region is where the 1960 Chile earthquake of magnitude 9.5 happened, the largest earthquake ever recorded. While the northern portion did not slip in 1960, so in the southern region, the plate is still slipping very slowly, while in the northern region, the plate is locked. C. Cascadia. Here are the plate motion vectors that are moving in the same direction as plate convergence. Why do you think they are all moving in that direction? Yes, the plate is locked in Cascadia, so we are in the interseismic period for this subduction zone. Here is a plot of the motion recorded at the subduction zone in Japan. These vectors show the difference between measurements taken before and after the 2011 earthquake, showing the motion of the fault during the earthquake. The convergence of the Pacific plate is to the west. What does this plot show? Yes, this plot shows that the upper plate moved eastward when the subduction zone fault slipped. This is a plot of GPS velocities for California. They are mostly all in a direction parallel to the San Andreas fault system. Think about this on your own if you want. We can discuss this in class. Here are plots of continuous GPS motion for two different GPS sites along the Cascadia subduction zone. The upper plot is from Cape Blanco, Oregon. The three plots are for latitude where north is up, longitude where east is up, and height where up is up. The lower plot is from Cape Mendocino, California. Take a look at the longitude plot. The values are decreasing over time. How do you interpret these data? Yes, since east is up and west is down and the values are going down over time, Cape Mendocino is moving west over time. Taking a look at the latitude plot, the values are increasing over time. How do you interpret these data? Yes, since north is up and south is down, the values are going up over time. Cape Mendocino is moving north over time. Here are some GPS position observations collected once a year for 6 years. In which direction is the GPS monument A moving? Let's plot these data to determine this. We will begin by plotting the points as they move in the north direction. Plot the first two data points using time on the horizontal axis and north on the vertical axis. These first 2 points go here. Plot the rest of the data points. This is where I plot them. We will next plot the points as they move in the east direction. Plot the first data point using time on the horizontal axis and east on the vertical axis. This first point goes here. Now plot the rest of the data points. This is where I would plot them. We will next plot the points as they move in the vertical direction. Plot the first data point using time on the horizontal axis and height on the vertical axis. This first point goes here. Plot the rest of the data points like so. Here is another data set plotted. Each data set has a positive slope. The numbers are getting larger with time. The upper plot is a north-south time series. The station is moving north. The center plot is an east-west time series. The station is moving east. And the bottom plot is a height time series. The station is moving up. Let's plot north and east together. Plot the location of the GPS station each year with east on the horizontal axis and north on the vertical axis. I show where the first 3 data points are plotted. Continue to plot the location of the GPS station for each year. Next, draw an arrow from the first data point to the last data point. What direction is your GPS monument moving? Yes, the GPS monument is moving to the northeast. Focus on what direction is GPS monument B moving? Focus on the data for the north data. Is monument B moving in a more positive or negative direction? What direction is GPS monument B moving, north or south? Now focus on the data for the east data. Is monument B moving in a more positive or negative direction? What direction is GPS monument B moving? East or west? Plot the location for monument B for the data from each year. Now plot the location of the GPS station for each year. Draw an arrow from the first data point to the last data point. What direction is your GPS monument moving? Yes, to the southwest. In this activity, you will work with GPS data to explore plate motion and deformation in the Pacific Northwest. By analyzing multiple GPS time series plots, you can determine the direction and rate of regional deformation. Part 1. Analyzing real-time series data to calculate GPS velocity vectors. This is the GPS time series for the SEAT site in Seattle. The first step is to calculate the average north position at the beginning and end of an annual time period beginning January 1st, 2007 and ending January 1st, 2008. Estimate the average north position at these two times by using the vertical scale on the left. I've entered what I estimate these average positions to be 12.5 and 15.6 millimeters. Subtract these two values to estimate how much the GPS site has moved during the year. What do you get? (15.6) minus 12.5 is 3.1 millimeters. Since this happened over a year, we can calculate the velocity by dividing the distance by 1 year. What do you get? I get 3.1 millimeters per year. The next step is to calculate the average east position at the beginning and end of an annual time period beginning at January 1st, 2007 and ending at January 1st, 2008. Estimate the average east position at these two times by using the vertical scale on the bottom plot. I have entered what I estimate these average positions to be at 14.8 and 18.2 millimeters. Subtract these two values to estimate how much the GPS site has moved during the year. What do you get? I get 18.2 minus 14.8 equals 3.4 millimeters. Since this happened over a year, we can calculate the velocity by dividing this distance by 1 year. What do you get? I get 3.4 millimeters per year. The third step is to plot the average north and east positions for the annual time period beginning January 1st, 2007 and ending January 1st, 2008. Use the graph paper where each block represents 1 millimeter. Plot an arrow on the vertical axis using the north velocity of 3.4 millimeters a year, and plot an arrow on the horizontal axis using the east velocity of 3.4 millimeters per year. Finally, draw an arrow diagonally where these two arrows would meet. See where the red arrow is drawn in this example? Note how one can draw the horizontal arrow beginning at the tip of the vertical arrow. This resultant arrow, or vector, tells us the direction and magnitude of motion for the time period, in this case a year. One may use the scale of the grid spacing to measure the length of this red resultant arrow to determine the overall velocity. Complete the rest of the plots for the rest of the GPS sites along the Cascadia subduction zone. Here are site Nia and Cedar. Here are sites P401 and P022. Here are sites PABH and SC00. Here are sites P407 and P430. Place this map over your plots one by one and trace the GPS site motion vectors onto this map. Do this by placing the origin of the vector at the beginning of the arrow at the label point for that GPS site. Place the tail of the vector on the point of the corresponding bubble and trace the arrow from your worksheet. Place the GPS station graph behind the map and then copy the vector onto your map. Then draw the GPS site vector at the same scale that you used for your plot on the grid paper. Do this for all GPS motion vectors. Part 3, questions. What do you notice about the velocities of the GPS stations and their geographic locations? How do the velocities at each station change from west to east? Which stations are moving fastest? In 500 years, how far will the stations along the coast have moved? What possible outcomes can you imagine if different portions of the plate continue moving at different rates over millions of years? Finish this lab and turn it in our next class.